Okay, let's get started. I'm Debbie Liu, Executive Director of eSig, and I wanted to welcome everyone to an eSig webinar. For those of you who are not familiar with eSig, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of clean energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working group, and task force activities, and we produce technical resource materials. And for those of you who are members, thank you for your support, and it makes these webinars and other work possible. For those of you who don't know, we'll be holding our fall technical workshop in Philadelphia next week, October 27th through the 30th. And we'll be talking about integrated planning with DERs. We'll be talking about large loads, artificial intelligence applications. Our workshops and our webinars are open to everyone, so please feel free to register anytime on the eSig website at www.esig.energy, or you can find us on LinkedIn, YouTube, Facebook, and X. So a few logistical matters before we get started. We're going to mute everyone's participant lines to avoid unnecessary distractions. For questions and answers, please go to slido.com and enter ESIG, ESIG 22, ESIG 22 as the event code. The instructions are also at the bottom of the screen. And on slido.com, you'll see a thumbs up button next to the questions, so you can cast a vote to help prioritize the questions that are submitted. And we'll plan to save time at the end for questions and answers. We'll wrap it up at actually in 90 minutes, because this is an extra long webinar. And we have an email with a link to the video file once that has been posted, and we will provide short responses to all unanswered questions after the webinar. So please don't be afraid to ask your questions through Slido. So today, we're going to hear from Avangrid about their work in flexible solar interconnections. As you may know, sometimes you want to interconnect a generator or a load, and it could mostly be interconnected reliably, except for, say, a handful of hours in which you may be overloading grid infrastructure. And even though it might be only a handful of hours, typical planning practices dictate that we upgrade the grid infrastructure, and that can be expensive. So sometimes projects get abandoned altogether for want of these few hours when grid infrastructure can be overloaded. Now, you may have heard of Australia's work in flexible solar interconnections as a solution to this problem. So today, we're really excited to present to you two demonstration projects in Avangrid territory in upstate New York that manage the distributed solar to avoid overloads, so they can essentially increase hosting capacity on their distribution system without the expensive upgrades that would otherwise be needed. And we're going to hear about experiences with these systems over the last 4 years. And I believe these were the first flexible solar interconnections in the US. You guys can correct me if I'm wrong. And we're really excited to have today Zach Caruso, who is a lead analyst in programs and projects in clean energy policy for Avangrid Networks. They serve nearly 3.3 million customers in the northeastern part of the United States. And Zach is responsible for leading DER management projects, including the Flexible Interconnection Capacity Solution, and he guides the DER management strategy across Avangrid's electric operating companies. And we also have today Leo Jiang, who's an associate professor and director of the Center for Electric Power System Research at Clarkson University, and also a principal engineer at Avangrid Networks. And then just this month started working here with eSig as an engineering fellow. And we're really happy about that. I've been very lucky to get to work with Leo since we were both at GE about 10 years ago. So just a short reminder once again, use Slido at slido.com with the event code of ESIG22 to ask your questions. And now, without any further ado, I'm going to turn it over to Zach.
Thanks, Debbie. I will just share my screen here so you can see the slides. get that done. Okay, so thank you for the introduction, Debbie. As Debbie mentioned, I am Zach Caruso, and I am a lead analyst of programs and projects in the Clean Energy Policy Group here at Avangrid. And I have been in clean energy policy, used to be called Smart Grid Innovation, but same. And I've been in energy policy since I joined the company back in 2017. And as you're about to learn, I've spent all of that time, all 8 years at this point, on flexible interconnections. And the project itself actually predates even my time at the company. So to Debbie's point, I don't like to brag, but I would say we were at least the first ones to propose and start a project on flexible interconnections, even if we may not have been the first ones to actually implement something. But to go into a little bit more detail about Avangrid as a whole, as Debbie mentioned, Avangrid Networks serves about 3.3 million customers across New York and New England. We have business primarily for electric in New York, Connecticut, and Maine. We also have gas business in Massachusetts, and we have gas business in those 3 states as well. Today, we are going to talk about our New York primarily, and that is at our NYSEG, or New York State Electric and Gas, and RG&E, Rochester Gas and Electric, operating companies that we operate here in New York. Kind of together with those 2 companies, we have a very large presence in upstate New York. We serve all the way from Brewster, kind of Westchester County, Putnam County, outside of New York City, kind of in the suburbs, all the way out towards Buffalo. We serve the suburbs of Buffalo, as well as we serve all the way up to the Canadian border in Plattsburgh, right along Lake Champlain. So we cover a large portion of the state. And what that means is that we cover a lot of open space, and that affects our DER adoption levels. And you can see in this data is even a little bit out of date, but you can see the how our amount of space and the amount of land available affects DER adoption and affects DG interconnection in our states. We see primarily capacity-wise, mostly large, over 1 megawatt, solar and a little bit of storage, more storage now, sites coming onto our system. So while we do see a high volume of small PV sites, by far the biggest capacity impact on the system are these large sites. And the big impact of that, the big sort of side effect that we have to deal with, is that those large sites kind of can eat up capacity very, very quickly, right? And so we get from a state where there's a lot of capacity available on the distribution system to a state where there is no capacity available relatively quickly. And some of these substations, including the one that we talk about today, have over 20 megawatts of distributed generation on them, and interconnected today. So that shifts the paradigm of how we've been operating as a utility quite significantly. So with all that in mind, we started to look at flexible interconnections back in 2014, 2015 timeframe. And that sort of has built us to where we are today. Was we recognized that we would sort of need to look at alternative approaches as we started to get to higher levels of adoption. But before I really get into the history of the project, I think it's fair to take a step back and talk about what we mean when we talk about flexible interconnection. And to do that, we actually need to talk about a different term that I like to use to kind of help with the explanation, which is what we call dynamic capacity. And the reason we kind of bring this dynamic capacity concept in is to separate it from what we call today firm hosting capacity. And that firm hosting capacity is the amount of DER capacity that we can interconnect sort of under a worst case scenario, being very safe and basically with a mindset that is more or less set it and forget it. More or less, the DG can come in, they apply, we study them in a way that gives us a ton of headroom and allows us to know that if we interconnect that DER, we set it up and they operate, that basically whatever they do within, a certain kind of operating parameters, right? They can't do anything crazy, but if it's a solar site, if they're generating at full output on the sunniest day of the year while 20 other megawatts are also generating simultaneously, we interconnect sites and we require upgrades at that stage, at the study stage, to our distribution system to know that we can accommodate that without having to worry about anything else, right? Without having to worry about, communication to the DER site, without having to worry about any sort of controls. It's sort of we'll take whatever you can give us, and we actually build the distribution system to accommodate that, right? So there's sort of almost, I don't want to say overbuilt, but there's sort of a mindset of we have to shift everything else to make that DG interconnect safely, and that's costly. But if we look at the distribution system over time, and we look at the amount of real capacity that we have on our equipment, thermal capacity, we see that at that, say the peak hour, that most sunny hour of the year, in the middle of July, the distribution grid actually probably has more capacity in it to accommodate additional PV or DER generation at that time, because generally those peak sunny hours, specifically we're talking about July, we are currently still a summer peaking utility. We probably have a fair bit of load there because it's probably a hot day and there's probably everyone probably has their AC on, and that load helps soak up some of that generation locally so that less power is flowing through whatever the constrained piece of equipment that we're talking about. And therefore, if there was additional PV capacity on the circuit, additional installed solar sites, they could output at that time and take advantage of that additional capacity. The challenge with that is that that capacity is not always there. It changes from hour to hour, second to second, minute to minute, because it's based off of the loading, which varies. And it's based off of loading, which also is hard to predict. So with that in mind, we kind of have this, and I can go into the detail, or I'm not going to go into the details of this example, but the point shows that if we have a certain a bank rating that is 10.5 MVA, we would only allow 7.875 MVA to interconnect firm to that, but we could have as much as 16 MVA available. So that's a big gap, and that's a big delta of potential that we can go over or install more capacity to be able to get us up into, or get us more PV generation, and that has benefits for the system, that has benefits for ratepayers, and ultimately it has speed benefits as well, right? If we don't have to build that upgrade to increase that capacity to get more DG on, there's advantages there. Or there's advantages that we can get sooner to that effect. So there are ways to do this via studies, right? By studying the sites in a way that gives you a profile that tells you, all right, so between these hours, my worst case scenario is this min load. So you can have X amount of capacity. And then at these hours in this bucket, I have this min load. And so then you can have this capacity. And you can see how one might break that out on the left here. But one thing I'll point out here is that depending how you slice those buckets, you still end up with a worst case scenario, right? So if I'm doing a summer, and I'm saying summer is from, say, May through September, right? I am in that bucket, whatever bucket I'm looking at. I'm getting both the very hot days where I might have a significant amount of capacity. I'm also getting those, particularly in upstate New York's, those cooler, 60, 50-degree days that happen to sprinkle themselves in May or in September that we would see kind of a lower min load. And so the benefit of this is that we do get more capacity, or that we're able to utilize, but we perhaps don't get all the way up to that orange line in this diagram. We don't get all the way to that dynamic line because we have to sort of build in these margins because we're not actively feeding back what that real-time dynamic hosting capacity is, and we're still relying on that study to drive what these operating envelopes are, or rather what these perhaps limited generation profiles are, as we see out in California. And it has, as I said, it has advantages, but it also introduces some challenges of now we have to manage those schedules. We have to keep track of them. If this site comes on and has one schedule, another site comes on, gets a different schedule, we have to be able to kind of dynamically or proactively take each of those schedules in and then include it in the next study, and then so on down the line. And then you get into concepts of like with storage, where they're very dispatchable. If you're giving them a schedule, how much are they utilizing that capacity they've kind of been allocated versus how much are they, and this is true with solar too, versus how much is it just kind of to be safe. And so you can very quickly kind of populate this additional firm capacity versus, again, if you're working to that actual value, you can operate to what is really there, and not to kind of what might be there, and have to work on these safety factors. I will mention, just for everyone's edification, we do not currently offer scheduled capacity in New York. And we are working on, we have default schedules for batteries, and we are kind of working on ways to integrate more sort of schedule-based processes into our DER interconnection process. But this is not something that we kind of do on the level that California has kind of adopted it, or at least kind of built the processes out and sort of laid the groundwork for, where any project can kind of come in and, in theory, go this route. And that really gets us to sort of the final point of this idea of flexible hosting capacity, right? Which is, now I can allow, if I have some sort of control system in place that is dynamically monitoring that constraint, assuming it's a substation thermal constraint, it's monitoring the current flow through the transformer bank, and it is dynamically feeding that information back, about how much capacity is available to the flexible DER on the circuit to allow them to be, their output to be curtailed if needed. And the thing that this does is that it basically, in theory, creates the ability to put as much DER as you want onto a location, because you have a feedback loop that will prevent that DER from going over your system capacity limits. So you will always stay, again, this is assuming like perfect performance, but you will always stay within those operating limits because you will always curtail that DER to a safe level. Now, in practicality, it's not practical to install 50 megawatts of DG on a 20 MVA bank because you're just never going to have that amount of capacity, right? Even though I could curtail it and be safe for the developer, it doesn't make sense to have that much capacity on because you're basically paying for capacity that's never going to be able to generate it. So obviously there is an economic level that we can get to where it's the amount of curtailment, right? The amount of energy that I'm getting out of the incremental megawatt is kind of equal to the cost to install and build and maintain that additional megawatt. And there's also, which I will probably get into at the end, there's also the idea of additional technical limits of, as a utility, I also don't want to have 50 megawatts of generation on a 20 MVA bank just for sort of fail-safe and N-1 reasons, right? That makes things more operationally complex, especially when I'm relying on a single control system to kind of back me up there. So there's operational considerations that also have to be worked in. But in a vacuum, we sort of get to this place where we can think about, or we have to start thinking about hosting capacity limits as actually an economic determination and not as much of a technical one, or not solely a technical one. And we would call that level sort of the flexible hosting capacity of that particular location. And for us, you can see how in that right diagram, how that increases the amount of DG capacity that's able to generate. And it's not just on the sort of the sunny days, right, where we're curtailing and where there's plenty of solar generation. It's actually on all days, because that greater capacity, that greater number of panels is going to be able to generate more power even on cloudy days. So the sort of rising tide lifts all boats in that scenario. And oftentimes, as in this scenario that I show here, that can be done with very little curtailment. And finding that sweet spot is actually kind of the key point of how much curtailment is accessible. But all we need to know is that this is the idea of flexible capacity, and that rolls into our idea of flexible interconnection, which we formally define as arrangements enabling more DER capacity to interconnect to the electric grid by utilizing utility-owned and operated real-time DER control schemes to automatically manage that DG or that distributed storage outputs to stay within grid constraints. Nothing new there. It's kind of just what I all described to you. But I think it's important to enforce that we, at least at Avangrid, separate flexible interconnection from that scheduled interconnection approach, just for purposes of conversation and development. We really see what you need for a flexible interconnection, this sort of real-time control and feedback and management, is fundamentally different than what you need to set up a scheduled firm interconnection. There are some commonalities, but sort of the scheduled interconnection is kind of an extension of a firm interconnection. It's just, more detailed study and a little bit more complex. A flexible interconnection is kind of very much its own animal in that effect. And as I said, it's dynamic. It has layers of protection. And the key point is that it's an alternative to grid upgrades, right? That under that firm interconnection scenario, the only way to go over that firm limit is to upgrade the thermal capacity of that transformer bank, to go from that 10.5 MVA limit to a 14 or to a 22. That's the only way that I can put more DG capacity there, because according to our planning constraints, to be able to accommodate them at any time under under all kind of operational conditions, that's what we need. That's what we need to have. We need to have a bigger bank to stay within those operating limits. And the reason, or that's kind of the compensation, or that's the value stream that is received by that customer when they agree to the flexible interconnection. It is that deferral of grid upgrades that they don't have to pay for. Because in New York, it's very much a cost causer, cost triggerer pays. And that is why we do not pay for curtailment in New York under a flexible scheme, because it's sort of, you're agreeing to a flexible scheme as a condition for interconnection. So, you're sort of agreeing that you're causing this problem and you're being curtailed to mitigate it. All that is to say, that's just background. Now to talk about the fun stuff. So in New York, we have the FICS or FICS Rev Demo, which, as I mentioned, started on July 1st, 2015, in response to the Rev track 2 order, I believe, that was actually filed back in 2014 that directed all the utilities in New York to file 2 demonstration projects. Being as we operate 2 utilities, we had to file 4. And so this was our project for both NYSEG and RG&E. And the implementation plan was filed in 2016. And ever since then, we have been filing quarterly reports on the New York DPS website. So if you are really interested in what I'm talking about today, you can go back and you can look up all of those reports and you can get the nitty gritty of the breakdown of how this all evolved. And as I mentioned, FICS stands for Flexible Interconnection Capacity Solution. And the point of it was to test this new model of flexible interconnection for interconnecting DERs in constrained areas of the electric grid. It utilizes a technology called Active Network Management, A&M, from a company called SGS, Smart Grid Solutions, that had actually, at that time, had demonstrated the technology in the UK with great success. And part of the whole process was that we were partnering with them to pilot it in North America, to demonstrate, to see how successful it would be, and demonstrate some of the New York and North American specific considerations that we had to include in order to make flexible interconnections successful. We ended up deploying 2 sites in NYSEG and RG&E territory, 2 schemes at 2 substations. The primary one of those that I'm going to talk about mostly today is called Spencerport PV, which is sort of a misnomer, but that's the name now because that's what we've been using, because there is a town of Spencerport around up here in Rochester, New York. These projects are not in it. They're actually in Ogden, technically, but which is the town and around the village of Spencerport. But it's water under the bridge. You get it where it is. It's in Spencerport, not Spencerport. But we also had a project up in Plattsburgh, in Champlain, New York, and that one we call Robinson PB. We'll mention it today, but most of the results that we talk about today will be from Spencerport. In addition to those sites, we also had other sites that expressed interest, but we were not able to accommodate them, or they just ended up choosing not to go forward with a fixed solution due to other barriers or kind of the nitty gritty and the ups and downs of DER interconnection in general. You have to deal with landowners, you have to deal with permitting. Projects sometimes disappear mysteriously and for a variety of reasons. So those projects were interconnected, the ones that we chose, Spencerport and Robinson, in 2021. Spencerport was commissioned in April of 2021. Robinson was commissioned in August 2021. And we've been operating them to this day for over 4 years, 4.5 years at this point, with, I would say, great success that I'm about to get into. And just to give a little bit more context on kind of how A&M works, right? It's kind of built on this defense in depth or layers of control methodology, where we have a trim threshold, right? And as I said, we're monitoring the current on the bank that's flowing through the bank. When that current goes above a certain limit, in our case, it's 85% of the bank rating, thermal rating, as I mentioned, the system will take action to curtail the PV sites that are part of the flexible scheme, and it will curtail them and continue to curtail them and trying to maintain them within an operating limit, within an operating kind of area, up until that current flow drops below and to a safe level where it can release all of the capacity back to the DER sites, and they can kind of go back to normal unconstrained operation. And I won't go into too much detail here, but know that it's more or less a pretty straightforward kind of control scheme. It's sort of just operating on a trip and release approach. And then in addition to that trimming, there's also a second layer, which is the ability to trip these sites, the DER offline, if the current were to reach a level that was 95% of the bank rating, which was close enough to the transformer rating, where we want to take action quickly, and where clearly the DER that we're controlling have failed to respond to the trim commands, right? They've kind of failed to play nice and nicely follow our direction to reduce their output. And we were forced to take more aggressive action and protect the system. So we trip them offline one by one to reduce that current on the bank. And as I said, very straightforward. And we can show it working. We can show it in action. This is an actual snapshot of time from Spencerport, actually. And you can see how this is kind of, I guess there's various shades of green, but the sort of like forest green line is the current on the bank, specifically the current on phase B. And we can see it go over the trim threshold, which is this darker green line up here. And we can see rapidly the system take action. And this lightish green line will drop down. It goes from a 5 megawatt, which is sort of the full capacity of the site. It drops down to just under 3 megawatts of maximum output. The site's output, which is this, like the darkest green line here, follows it, follows that max limit, and drops down as well. And we see how that also drops the current. And when the current drops below the release threshold, the system gives back some capacity to say, okay, yeah, I curtailed you too much. You can have a little bit of that capacity back. And then it sort of allows the site to operate in this limited output. And it's slowly giving it back capacity over this time as it's saying to kind of operate in this sweet spot between these two lines. And you can see that by this light green line moving up and up and up. And then we can see that actually this drop at the end, this is not us curtailing it, because you can see that this line remains the same. This is from a cloud going over. So once that cloud goes over and all the flexible PVs, as well as all the other PV that's on the circuit that's not flexible, as their output drops, the current flow through the bank drops precipitously as well. And when that happens, we say, okay, yeah, you guys can go back to kind of full output from your PV sites, because we don't need to be curtailing you anymore. There's plenty of capacity for you to use. And ignore this. This is out of date. They have actually been curtailed more than this. So just to kind of go back into the history of this, the approach of this project, right? We've been, as I said, we've been working on it since 2015. And we went through some trial and error. We had some certain thoughts about what would or wouldn't be a viable project. So we approached a number of different sites throughout the process of this project. And we definitely learned some things from which ones were successful and which ones were not. Mainly, we learned that voltage issues, which we targeted with our first DER and with some of these subsequent DERs, generally the cost of the mitigations for that are don't really justify and aren't commensurate with the value gained from the flexible interconnection. And sometimes those constraints can actually require a significant amount of curtailment to control the voltage sufficiently to stay within our ANSI limits. But so that kind of created a lot of challenges when it came to implementing voltage-based flexible interconnection. And so that's why we have kind of moved forward with thermal approaches for the most part, as Spencerport, which is on station 113 up here, that was a substation bank thermal constraint. And we can see the cost difference between the voltage issues, the voltage constraints here, and those substation thermal constraints. We can also see um, the general kind of dropout rate of a number of these projects, right? Most of these projects that did not choose flexible also did not choose a static interconnection, right? So that would indicate that not only was flexible not viable for them, neither was the static approach. So when it comes to kind of comparing the two, we think that or we feel that that's a good demonstration that while we did talk to these sites, they didn't end up choosing flexible interconnection. Flexible interconnection is still a viable option if we can find the right site, as we did with the Spencerport sites. So keeping going with that and kind of jumping to the point is this is the total amount of curtailment that we have seen from that constraint, from that thermal constraint for the Spencerport PVs. You can see in the early years, 21 through 22, we didn't see any curtailment at all. It did not curtail once. And you may also know that 21 and 22 was kind of COVID times. So there were some changes in the load profiles of the circuit. There was actually some issues with the PV sites themselves. There was some downtime at certain times when we would expect curtailment to happen. That likely led to us just never crossing that threshold until 2023, when we sort of saw a spike. Not a spike. We saw our first curtailment event, I should say. And since then, in subsequent years in 2024 and in this year in 2025, we have seen increased curtailment. I will make the final point here just to point out that when we're calculating curtailment, we're sort of projecting out, and we're kind of calculating it over the total amount of energy generated in a year. Generally, when we get curtailment, it happens in the shoulder months. So the amount of curtailment that we see percentage wise is going to be higher at the beginning of the year because we've in April, May, we see a lot of curtailment. And so by the time, it's June, July, a greater percentage of the total generation that we've seen has been curtailed. But once we're through summer, once we're through winter, assuming that there's little to no curtailment in that times, those numbers actually drop. So I would say that we expect to probably see 2025 fall in line or close to 2024 of about 0.1% curtailment. And I'll also point out that the estimated curtailment that we told the developer when they interconnected was 0.27. So while 0.1 is small, it's actually even less than what we estimated, but it's close, right? We're in the ballpark, especially with the conservative assumptions we took when we did that study. And then finally, or in addition to that, we actually have to look at the total amount of curtailed generation that we see, because one of the big takeaways we had from the project was that when you set up a control system that's monitoring these PV sites and it's monitoring the substation, if you lose communication to any piece in that control algorithm, in that control scheme, you have to take fail-safe action in order to reduce the power output of the PV sites to protect the system. Because as things are set up today, and Leo's going to go into a little bit more detail of this, but as things are set up today, we don't know when we're going into fail-safe, what time of year that is, what else is going to be happening on the circuit. So we have to take the most conservative action and reduce the power output of that flexible PV to the maximum amount allowable under a firm interconnection. And so in the case of these PV sites, there's 15 megawatts total, but that firm allowable is about 7.6 megawatts. So you can kind of see how if I'm doing that every time I have a communications blip, of a couple minutes, or every time there's, there's a little, we have a little like loss of comms event, like a cell tower goes down or something like that. Um, that can kind of stack up. And there's other events that are built in here as well that have to do with kind of more operational things of, if a site gets curtailed or gets tripped offline, I should say, then there's a process that we have to go through to make sure that everything is safe before we bring them back on. There's travel time of personnel that have to go from their home base to these locations in order to, diagnose and make sure that everything is safe. And so, this is something that we have to build into our assumptions when we're bringing these sites on. We have to be clear and honest that you're probably going to see some additional curtailment. That's what we call non-network curtailment. That's not directly due to the constraint existing, due to us having that power flow through the bank that's over a certain level, and is more due to just these sort of operational challenges and just the practical considerations of operating these sites. But to put that in context, those losses are kind of on par or even less than sort of just general loss of generation from outages and both utility and customer outages, and equipment failure and stuff like that. So it's not so out of the realm of kind of reasonableness, that even for these sites, which are our first sites and kind of where we're getting our feet wet with how we operate these sites and the various challenges that come with that, and making those things more streamlined, the amount of curtailment is manageable when all things are considered. I'm going to run through these lessons learned because I've kind of covered most of these, and I want Leo to have time. But one of the big things we learned is that interconnection takes time. Like I said, we started this in 2015. We didn't commission any of these sites into flexible interconnection sites until 2021. There were permitting delays. There were contracting delays. There's just a lot that goes into it, and it's not we can get PV sites in 6 months and then we can interconnect them by the end of the year. These things just take years and years to go through the process, and so we have to take that in mind when we're designing these demonstration projects, that it sometimes takes us time to get actual kind of lessons learned and actual on the ground experience with these things. We also saw that developers were willing to accept curtailment. They agreed to be curtailed and be a part of a flexible scheme instead of upgrading those substation banks. So it is something that developers and large PV developers specifically are willing to accept in certain situations. Now, the guardrails on that, I think, is a bigger conversation, but they will do it. And I think that's positive overall for the expansion of this technology and the expansion of this approach. And I kind of talked to the site selection stuff, right? The other thing is that anything below 5 kV is probably not going to have that much capacity anyway. So better to focus on higher voltage circuits and feeders, just for sake of trying to get the most bang for your buck here. I talked about non-network curtailment, and I talked about the source of loss generation, that it's more than just non-network curtailment and flexible. There's lots of places that these PV sites kind of lose generation that they're not able to generate. We kind of did some very basic curtailment analysis at the beginning of this. It's actually still very simple, but there's kind of more advanced methodologies that can be used. We can integrate forecasting. We can integrate sensitivity analyses. We can even integrate a more probabilistic approach into our curtailment analysis methodology to perhaps give a clearer picture of the curtailment risk that a customer might be experiencing. There was some significant challenges when we were connecting these sites having to do with the DER gateway, which is our piece of equipment at the site that is sort of the local controller for us. It's able to trip the customer offline at the recloser, like I mentioned, and it's what's passing these limits to that PV site. And we had a significant challenge with actually getting that to work and work consistently and reliably, because there's not really standards. There's not really great kind of understanding of what is needed to accomplish this, at least at the time that we were implementing this within that community. And so we kind of had to work through that in depth in order to get these sites up and running and have them kind of operating reliably with the getting those signals and then curtailing and actually curtailing to the level we asked and not curtailing like half the inverters. And then we go, well, you didn't curtail all the way. And so we start tripping them offline because they're not complying with our set points. And we've also kind of talked about, or I mentioned briefly, the 75% rating for thermal capacity. When you start working with flexible interconnections, you can move those operating limits closer to more of an operational limit, right? To how much loading am I comfortable operating this transformer up to, and less of a sort of planning, I need to leave space for small DG type of approach. And so we use 75% for our static ratings, but we're able to actually go to 85% of the rating for flexible. And so that kind of gives us a 10% capacity bonus just by moving to flexible, right? That capacity is free, and there's no curtailment associated with it. And then recommendations. We are currently working to expand our flexible interconnection pilots. We're hoping to have something put in by the end of the year, filed to expand our rev demo project to additional substations. And that's going to involve putting together a detailed flexible interconnection process that's integrated with the current SIR process. We're going to target specific locations, because one of the things we did here is we targeted applications. We kind of looked and were screening for projects as they came in. And when we found a good one, we kind of went after it and pursued it. And you can see that kind of had mixed success. Going forward, we're going to take more of a field of dreams approach, where we're looking to kind of say these 3 locations are eligible. We'll take applications for flexible interconnections here, and we're going to just kind of interconnect whoever we can, kind of whoever is able to kind of first come, first serve. And we feel that might be more time efficient, because if we're kind of grabbing projects as we go, the hit rate is sometimes less than would be desired. We're exploring opportunities at subtransmission, developing a standardized interface for that utility DER gateway to DER communications interface that we require to do this. And then kind of as a segue, explore technical improvements to our forecasting and seasonal capacity limit process, our seasonal capacity limits that we use to reduce that non-network curtailment, to try and provide some intelligence when we're doing that non-network curtailment. We're bringing those fail-safes in that allows these sites to still be able to operate up to reasonable levels. And with less further ado, I'm going to throw it over to Leo.
Thanks so much, Zach. Yeah, you can go to the next slide. So basically, if you look at the flexible interconnection, the demonstration project, and then the curtailment is really, really dependent upon how much capacity you have and how much room you really, what's the threshold you're using in the controllers there. One of the biggest concern from the developers is how much curtailment I will be facing in the flexible interconnection. So this is just this study is done at Clarkson. We are in collaboration with Avangrid in the last 2 years, trying to see what the ways we can improve the flexible interconnection, reduce the solar curtailment for the developers. One of the aspects we are trying to see there is, what is the rating of the asset? For example, for the transformers, If you look at the nameplate for the transformers, look at the manufacturers there, the transformer rating indeed is designed, the number is really provided or given under certain conditions. For example, transformer in general, they are rated for a specific ambient temperature, typically is a 30 C. Then depends on what type of transformers, which year they are manufactured, they are based on a certain average the winding temperature rise. Some units are 55 C or some units are 65 C. The modern units are primarily the 65 C. That's for the insulation levels you have. And then really the limiting factors for the thermal loading of the asset, for example, transformer, is indeed the hottest spot temperature rise. Usually the modern units are 80 C. That's the usually where your transformers are really specified for. Then there is a number of the loading capabilities, RTB standard, and I will not really list all of them. But one of those is RTB C57.91. There are multiple versions, and a lot of the utility or some utility as far as I know, they are using the older version, like for example, 1984, the version for the loading criteria, particularly. There's a sections we'll talk about the loading capabilities versus the ambient temperatures. In general, the loading capability of transformers will change like roughly 0.5% to 1% per Celsius deviated from the specific ambient temperature, for example, 30 C degrees. In the RTB standard, there are some recommendations. One recommendation is that you don't really need to run the thermodynamics trying to see if your ambient temperature, for example, is 10 Celsius, how would that be increasing the thermal capacity of your transformers? If you look at the figures here, the blue line is a conservative, the thermal capacity of transformers that are following the RTB standard. Indeed, this blue line is even more conservative than the recommended conservative practice of the thermal capacity of the transformers. So what it says there, the blue line, if your ambient temperature is 24 hours average, that temperature is below 30 C, you gain 0.5% of your capacity per decreased ambient temperature. There's a full blown of thermodynamic simulation documented in RTB C57.91. If people are interested, I will encourage you to really look at the standard that has more than 100 pages. There are some of the consulting firms and the research institute have been implementing the thermodynamic model from the RTB standard and the benchmark with real data. The short conclusion from those studies is the thermodynamic modeling to determine the capacity of the transformer is still in the conservative side, which is great. From the utility application perspective, we'd love to see the result is conservative, but still go beyond our static capacity. If you look at the figure here, the dashed green line, that's the static asset rating, which is 22.4 MVA. Next slide, please. So we did some study. We're using the ambient temperature historical data from the Rochester, New York, which is the Spencer port, the PV is located, the demonstration site. And then the left figure here is the ambient temperature distributions. If you look at that, we are in upstate New York. We have a pretty harsh winter with low temperature. That's why we stay in the rank more than other places. If you look at the ambient temperature, the average, just look at the middle bar there, we do have, like for example, from November to March, the average temperature is really like around 0 C degrees. And even though in the summer we have the average maybe in the July could be a little bit hot, a little bit more than 20, but a lot of the month we do have a pretty cold weather here. And then as Zach talked about the flash interconnection demonstration project, the majority of almost all of the curtailment are in the shorter month. which is March, April, May, and September, October. If you look at those months, the ambient temperature is fairly low. I mean, not fairly low, but definitely lower than the 30 degrees, that which is the rated ambient temperature for the thermal capacity of the asset. This case is the transformer. Now we're using the historical data here. We're using the following the RTV standard. We did both. One, the right upper right, that figure is we didn't do the offside. What I mean, the offside means that we do the average temperature. We also do increase the ambient temperature by 5 Celsius, the offset, trying to be more conservative. So that's the two scenarios that the result documented in the right side figures here. If you have the 5C offset temperature as a safety margin, you're definitely your thermal capacity, dynamic thermal capacity for the transformer will be shifted lower. But regardless, if you look at the bottom right, the figure there, the dynamic transformer rating will be much higher than the static 22.4 MVAs for the side. If you look at the shorter month, like March, April, May, September, October, you look at that, the transformer could easily gain a few megawatts, the capacity, because the lower temperatures. So basically the transformer capacity gain can be real, and then the gain can be location dependent. You don't really anticipate the similar benefit if you move in the southern states. But in obviously New York, yes, we definitely will see some of the additional capacity we have. Next slide, please. We also did that for conductors. I think the dynamic line rating has been more demonstrated on the transmission network. But if you look at the same principle for the conductors, there are ambient temperatures that could be wind speed, that could be solar irradiance. They all will impact the thermodynamics. At the end, is about your temperature gain of your conductors will limit the thermal capacity of the conductors there. I'm using the 477 all aluminum conductor as an example here. We're using the year 2023 data near Rochester. We're trying to do the thermodynamic study for the conductor thermal rating, both for the with wind speed and the without wind speed, trying to see what is the loading current the 477 AAC conductor can bear. Just for the comparison here, currently Avangrid uses 605 amps. The summer, the current for summer rating uses 810 amps. The winter rating for 477 AAC conductors. Now, if you look at the figures on the right, and the that's with and without a wind speed, what is the maximum current the conductor, the same conductor can bear? And then if you zoom in the yellow there, that gives you the figures in the left bottom there. You can see that even in the hottest summer time, the current, the bearing current of the conductor can go beyond 605 amps. That means if you are in the flash interconnection, if the main lines or feeder circuit could be the limited element, and then the acid rating, dynamic acid rating for the conductor, then you can get an additional capacity there. Next slide, please. We did this study for the Spencerport site. As Zach already illustrated, we really don't, when the demonstration, Avangrid doesn't really see a lot of curtailment. And then for some cases, we do have the thermal constraint curtailment. You can see that if you implement dynamic acid rating here, in this case, we're using the transformer rating, by the way. So the red and the blue, they're the before with the static, with and without dynamic transfer rating. For this case, we can see that with additional capacity, ideally, the curtailment, the network congestion related curtailment can disappear. But regardless, the curtailment like this for the 2034, that's what we analyzed, is the curtailment itself is low. There are multiple reasons contribute to the low curtailment. I will not talk all about that. Like for example, Zach talked about like originally when the study is using 75 CNR rating, but in the implementation, they go to 80% or 85%. That is the controller settings that implemented. So what it really says is here is that dynamic acid rating can increase the DER hosting capacity, can reduce the curtailment in the flash interconnections. But this is the study is that dynamic acid rating is really in the normal operational mode. When I say normal means there's no communication outage or loss of communication there. Now that's what I'm going to talk about next slide, please. Now this is the fail-safe mode. So for example, if the smart inverter local controller loses the communication with the central controller here, like in the figure, you lose that the communication. Currently the controller will do there is they will use the static allocated hosting capacity for the curtailment. That's trying to protect the grid asset and make sure that when there is no communication, your smart inverter will be really operated output as limited by the static hosting capacity there. For example, if you look at the figure here, for the second solar there in the middle, the static hosting capacity allocated to this side when there is a loss of communication, the smart inverter can output a maximum at 2.6 megawatt. For the third solar farm at the bottom, the allocated static hosting capacity is 0. Because as Zach said, for this side, the static hosting capacity indeed is 7.6 megawatt. And then we are following the last in, first out, the LIFO scheme, curtailment scheme. The first solar flex solar at the top, here it has allocated 5 megawatt static hosting capacity. That's why even there is a communication outage, the first solar farm, flex solar farm, will not face any curtailment because they do allocated 5 megawatt static hosting capacity. Now the question comes to, what if we know the load is 3 MVA or 3 megawatt? Now you know that you can use the load profile sort of to update this static hosting capacity to come up with dynamic hosting capacity. Using that number to update the controller. Now you may ask a question, we have a communication outage, how can you allocate? Remember, the local controller here will communicate with central controllers here frequently. And then for this demonstration side is every few seconds. And the other utilities are using every minute or so, but still the communication is still frequently until you lose the communication. So the data exchange before you have the communication outage, you still have that data. And of course, we always want to be conservative. Now that's what we will talk about soon. But so basically, you don't really, for the load, how do you know the load? You can use a forecasting plus a safety margin, or you forecast a load and put some other additional conservative forecasting result to update your static hosting capacity. Then that will configure the load controllers there. So if you have the 3 megawatt, for example, the load, you know that you can update the static hosting capacity to be dynamic hosting capacity. Then your second solar farm will be the allocated hosting capacity will be 5 megawatt because your total dynamic hosting capacity now is 10.6. That's why the second solar farm, flash solar farm, now that can allocate 5 megawatt hosting capacity. In the third solar farm, instead of 0 megawatt hosting capacity, you can have 0.6 megawatt hosting capacity there. Next slide, please. For the Spencerport PV site, we did some study there. From the improvement of the curtailment, we could integrate the dynamic acid rating in the normal operation mode. Indeed, we can, in the fail-safe mode, we can also integrate the dynamic acid ratings. As I said, like, because the local controller and the central controller, they communicate with each other very frequently. And on top of the dynamic acid rating, you can also have the already forecasted load to update the dynamic hosting capacity for the fail-safe mode curtailment. Indeed, from the demonstration project, the majority of the loss of communication, they're fairly short. That's why sometimes you will have a short-term load forecasting to dynamic update that the dynamic hosting capacity is indeed is enough. There are some occasions that the loss of communication can be a little bit long, but majority of them are pretty short. Indeed, they can be as short as a few seconds, right? That can confirm that. But yeah, the next slide, please. This is why it's a little bit busy slide. So basically, we did a number of scenario study. We use and compared to the state quo, which is the red bar in the left figure here, which is static transformer rating. That's currently what it has been implemented. And then the additional study that we did is based on all the real data we have, trying to understand if we have different combinations of how we update the static hosting capacity to dynamic hosting capacity into the flash interconnection controllers, what it means for the curtailment here. But this one is really in the fail-safe mode control. Then if you compare the red curve, the red bar to the blue bar, for example, the blue bar is the static transformer rating plus daytime mean load. For this side, I think daytime mean load, if I remember correctly, is about 3 megawatt, roughly. So that goes beyond roughly 3 megawatt, I think it's 2 point something. Then your second solar farm, because it's 7.6 megawatt static hosting capacity, if you plus about the 3, you basically, in the fail-safe mode control, the solar farm 2 will not really face much curtailment because it has the limited 5 megawatt output, which is the maximum output from the site. And then the further, if you look at let me see, if you use the static transformer rating plus forecasted load, this side also will almost get rid of you use the dynamic hosting capacity for the curtailment, you get rid of the curtailment part. In our study, we also put the 2C temperature safety margin when we do the forecasting, just trying to accommodate any forecasting inaccuracy. On top of that, we also put a 1 MVA safety margin together. So make our analysis very conservative, which, as I said, from the utility implementation perspective, we would like to go conservative. But here, the only difference is that we want to be reasonably conservative. So basically, incorporating the forecasted load in the dynamic hosting capacity, reduce solar curtailment in the fail-safe mode during the loss of a communication event. Next slide, please. I think that's all from my end. I will turn back to Zach. Muted. You're muted.
Yep. Thanks, Leo. And it is very interesting to kind of look at the impact of dynamic line ratings and dynamic thermal ratings on curtailment. But I also wanted to reinforce Leo's statement about the need to be conservative. And that's kind of the big challenge with talking about adopting these things, is trying to figure out the gap between, okay, yes, technically we can push it to this level, but one, can we reliably do that, right? Can we reliably say that, do we trust the data? Do we trust the temperature data enough to do that? Do we, are there other finer points that we need to take into account that in order to kind of, be conservative here? Example is wind data, right? To actually have the wind flowing over a specific segment of conductor, I think would be quite a challenge. And so you'd have to build a model that's kind of based off of the wind measurements where you're getting it, and then correlating that to the thermal impact at the section that you're talking about. And then once you kind of get that model, you have to start talking about, do I want, what level do I want to go to, right? We start talking about duty cycles and loss of life, and stuff like that, right? So that's kind of the big challenge. And there are definitely potential benefits, particularly to, having a more intelligent fail-safe threshold, just overall, right? Finding some level does get you significant benefit, right? Finding, even if it's going from all right, in the middle of winter, when I know I'm not going to be at full PV output, can I give more capacity back in fail-safe versus the summer, right? And the answer is yes to Leo's effort. The question is how much, right? Can I go from 7.6 to 9.6 or 8.6, or can I go all the way to 15? Which the developers and probably some folks would say, yeah, you should go to 15, but we have to be very, very careful when we're doing that. And we also have to think of that worst case scenario. So I did have a couple more slides here just on principles of access. I'm not going to go into those because I see that we have about 20 minutes left, and I wanted to give time for questions and answers because we all know that's the fun part. So I'm just going to stop there, and we can go into Q&A.
Great. Thank you so much, Zach and Leo. That was really fascinating, and I learned a lot. And I'm just amazed at, I think probably everyone is just at how little curtailment was needed for the flexibility, for the thermal overloads, and then also just looking at, this idea of sort of like using grid enhancing technologies on the distribution system, basically, to try and look at higher loadings during colder weather. So yes, there's a lot of questions. The first one is, if some of the PV units are able to dynamically control their output, that is reduce when the feeder is exceeding the limit, would you then allow them to interconnect? So not sure, maybe what they're meaning is if they're dynamically controlling their own output, maybe without your control.
Yeah, if I'm understanding the question, I think the challenge there is how are they getting that information, right? Because I think what's being proposed there is the same thing as what we're doing. We're providing them a maximum output and they're responding to it.
All right. Okay. How about the cost of the real-time management? Is it economical to implement based on your experience?
Yeah, I would say yes, in that we were able to get a developer to agree to cover those costs for that substation. And we are optimistic that future developers will as well at different additional substations. Because that, and if you want more detail, we put an intermediate summary report out last July that goes into a little bit more of this detail, but the cost of a bank upgrade is millions of dollars. The cost of this control is hundreds of thousands. So there is significant savings in that. The part that we have to deal with is like the ongoing support and the management of that. Who's paying for that, and how are we making sure that we're not we're kind of maintaining the cost causer pays mentality.
Okay. Someone asks, why only substation thermal limits used as constraints? How about voltage violations, voltage variations, protection, miscoordination, etc.?
Yeah, that's a good question. And I think I touched on it briefly, but to be clear, the reason we're targeting those substation constraints, and we've had the most success, is we believe that those are the most expensive ones to mitigate. A voltage violation, generally, not all the time, requires about a $200,000, maybe $300,000 mitigation. And so mitigating that is much less the business case is much less clear when we talk about a flexible approach, particularly using that as the driving constraint to implement flexible interconnection. It is definitely dodgy. And we saw a number of customers that had voltage constraints as their primary driver end up dropping out. Because the other thing that happens is when you start targeting voltage constraints, you might say you're mitigating like an express feeder or like a reconductor for like a voltage variation. We had a customer that we were doing that for, and the second you do that, you start introducing other voltage issues, right? You say, okay, well, I'm not doing the upgrade to mitigate this the steady state voltage issue, but once I put that PV on that circuit, now I have a bunch of flicker constraints popping up or a bunch of voltage variation constraints popping up. And you can, in theory, stack those on top. But at some point, I think you reach the megawatt hour that broke the camel's back, right? At some point there's too much curtailment there to make it feasible. I wouldn't rule out voltage in the long term. It's just right now we're kind of going after low hanging fruit, and that has seemed to be so far thermal constraints primarily at the feeder head and at the substation.
Okay.
And also, I just want to add that for the solar interconnections, we have to also adhere to the Avangrid interconnection standard with all the policy, with all the procedures there. Basically, even though the solar farm in the flash interconnection, basically the flash interconnection is on top of the traditional interconnection procedure that has been followed.
Mm-hmm. Thanks. Stephen Browning, who from the UK with the NISO, is asking, if you have multiple installations on one substation, what's the order for curtailment? Is it last in, first, pulled back, or bartering?
That's a great point, and I was going to cover that. So the ones that we deployed are LIFO, so they are last in, first out, and we found that to be successful. Provides the initial sites certainty or greater levels of certainty to their curtailment in the future. But long story short, the sort of the theory, right, and you can set up a lot of scenarios that shows that pro rata is really the way to go if you want to maximize the amount of a generation you're able to get on. And there's a lot of discussion going on in New York about this, where we've kind of had a number of stakeholder sessions about curtailment certainty, as pro rata definitely provides increased curtailment risk. If I'm the first site and I have to consider the chances that I'm going to have to share curtailment with future sites. And sort of to combat that, what we're proposing right now is a capacity quota approach, where we would establish sort of a maximum amount of capacity we would accept. And that sort of provides both a technical cap, right? Like I said, we don't want 50 megawatts on a 20 MVA bank. And it also provides some degree of curtailment certainty that we think is necessary to continue to implement these sites.
Nice. Thank you. Someone asks, is the hosting capacity defined per node?
So technically, dynamic hosting capacity could be defined per node. As mentioned previously, we're only focusing on substation and feeder level, sort of feeder exit conductor level constraints. So it wouldn't make sense to define dynamic host capacity per node, partially because you'd also need to have monitoring or some way of tracking that to be able to define the dynamic capacity at every node.
Good point. See, someone asks, are there autonomous controls required that kick in if an unplanned event reduces available hosting capacity?
The short answer is yes. The system is based off of the real measured current through the bank. And the advantage of that is that regardless of whatever else is happening, if it increases the power flow through that bank, reverse power flow through the bank to the threshold, the system will start curtailing. And so that can be any sort of scenario that does that. It'll take action.
Okay, thanks. Stephen Browning has another question from the UK. Obviously, this active network management is needed to secure the system, from the premise level to the transmission level. So is the TSO to DSO to customer in parallel with the market? So I think he's asking maybe about the coordination and the market operations.
Maybe the short answer to that is no, we haven't.
Okay.
Yeah, I mean, the longer answer is that we haven't needed to, because the way the
Right.
market is set up today, that compensation is really sorted out at the distribution level, and it is relatively static, right? There's not any wholesale dispatches or wholesale events that have to be coordinated with regards to these PVs. They are really just generating whenever they want, whenever they have power, and being compensated for it according to a set scheme. So certainly as this proliferates and as market rules evolve, that's going to become a greater importance. But today that hasn't been something we've had to integrate, because there's just no need to coordinate that transmission dispatch or that higher level dispatch or market dispatch with the operational needs of the system that are these constraints.
Just trying to provide a little bit the status in New York State. By the end of last year, there is only one DR side that has been participating in the New York State market, administrated by the New York guys. So just trying to provide a study call about the status about the DR in the market side.
Great, thanks. Someone asks, should we provide a set point to each DER during curtailment to minimize fluctuations?
Yeah, we are. So that's the that threshold limit, or that maximum export limit, is that set point that they're supposed to meet. And if they do not meet it within a certain tolerance level, the local gateway starts taking action to trip them offline, because the security of the system is always prioritized. So if we're telling you to respond, regardless of if it's a network curtailment event or a non-network curtailment event, and that site is not following our direction, then that's a risk, right? We now have an uncontrolled site in a situation that could cause system violations. And so we take action right away to trip that site offline if they're not following our set point.
Thanks. Someone says, interesting work you guys are doing. However, regarding dynamic asset rating, how do you validate the safety and longevity of operating them at dynamic ratings?
That's also a very good question. And I have to admit that when you operate any asset at a dynamic rating there's a certain level of risk you need to tolerate. And then even including if you go back to the RTB standard, if you look into the operational practice that has been used for dynamic line rating, you basically first, how much risk you can accept. The second part is if you want to do the dynamic asset rating, as I said in the slides, we would like to be more conservative. You need to put a sufficient safety margin to build that confidence when you're trying to operate the asset dynamically. And then I think at the end, remember, a lot of utility we're using summer rating and the winter rating. The winter rating will be increased compared to summer rating. There is a certain risk that utility adopted to get the winter rating, right? So that's just that principle. I think no matter for flash interconnection or for other planning or other study, interconnection study, that principle should be consistent across all your practices. So I just want to say that there is a certain risk. Yes, I agree.
Great, thanks.
And I would just throw in there that we do sort of asset health monitoring as we go here. So
yes,
you would see effects like that, and hopefully you'd be able to correct for it. Obviously, you'd want to avoid having loss of life on the transformer because you're kind of made the wrong guess with regard to your asset rating. But I don't want to say that's entirely trial and error, but there's processes in place that would hopefully catch that stuff before you got into a danger zone.
Mhm.
Yeah, some of the substation you will have the DGA integrate SCADA DGA there, and you can even have the temperature sensors in the sort of small cabinet of your asset that will real-timely measure your the critical signals that you can integrate that one into potentially you can integrate that into the controller as well. So that definitely you will have a layers of protection to make sure that your assets are safe.
Okay, thanks. James Ornstein asks, do you project increasing adoption of behind-the-meter storage to reduce curtailment?
That's the question is whether we're sort of doing that intentionally or whether that's a side effect, right?
I think it's
Today
a
there-
side effect, probably.
Yeah. So I think there's not a market for curtailment reduction. I would say that there's kind of a natural fallout or natural effect of doing this, because once I'm getting curtailed, I'm losing revenue that I'm not able to generate. I naturally have an incentive and there's a dollar value that I can now use and compensate others to reduce that. There's an argument about, is that leveraging kind of negative market dynamics, right? Is that value that I'm getting compensated really the value if I'm getting curtailed? Maybe. You do have to worry about transmission level constraints and local constraints. But all that being said, there is value if I'm that generator that is being curtailed to me having storage, right? There's definitely value for that. And there probably is value for compensating someone else for having storage. How you structure that market and how you kind of lubricate or grease those wheels to make that happen, that is kind of a bigger question that I think we have to get into once we have more adoption of flexible interconnection.
Sure. Thanks. Stephen Browning has another question from the UK. Conventional landlines going to fiber to the premises and the cell system are not fully robust. How about using data via power line for reliability, like power line carrier? Like use your own wires for the communications.
Yeah, I mean, I think it depends on a lot of that just depends on how much bandwidth we need, what are the exact requirements. I think we're really open to all solutions. For this, we're using cellular, but we have plans to use fiber where possible, where feasible. And if there's other solutions that we find to be more robust, we can definitely move to those, but I don't think any solution is going to be 100% reliable. And so we have to design whatever solution we're using to be sort of this fail-safe robust, right? What Leo's talking about. We're having more flexibility with that, no pun intended, kind of helps us overall because we're just never going to be able to get to 100%.
Someone asks, do you see any role for these DERs to provide voltage support?
I mean,
Maybe-
already we're enabling volt var. And so they will provide voltage support kind of dynamically going forward. And that's sort of a public good that benefits everyone. And that's kind of what 1547 2018 was sort of built around. But providing more dynamic voltage support based on voltages on the system that we observe requires us to be able to see those voltages, have visibility on them, and able to kind of operationalize that support. And I would also say that go back to the point about value, right? What is the value of that support? If I'm deferring a $200,000 regulator, there's some value there, but how much value, right? Is it worth it for the generator to be doing that if I'm paying them, $10,000 a year for that or something like that, right? I don't know. I'm not on the developer side. I don't know what their economic models are.
So basically, the small inverter configured as autonomous VOVAR settings that will provide the voltage control, but just not in the flat. So basically, Zach, the point is that really worth it in the flash interconnection? Just curtail the solar to mitigate the voltage issues. The economic may not be a lot viable for most of cases there.
That's super helpful. I'm realizing that we're at the end of our time. We're going to need to wrap up. I really want to thank Zach and Leo for the presentation today. As I mentioned earlier, an email is going to go out to all the participants once the video file has been posted. We're going to answer all the questions we didn't get to. We're going to get them posted as quickly as possible. And we really appreciate everyone's engagement. We look forward to seeing you again soon. Perhaps at our workshop next week in Philadelphia. Just go to esig.energy under events to get more information. And Zach and Leo, again, thank you so much. Really timely, really informative, lots of great engagement. Thanks to all the participants for their interest, and look forward to seeing everyone again in the future. Thanks.
Thanks so much. Bye.